Hello everyone, welcome to the second session of Signals and Systems class. Today let's discuss about classification of signals into different categories based on their characteristics. So this table is showing you the classification of signals into different categories based on their properties. So we can classify the signals based on their behavior, based on their independent variable, based on their value and so on. So based on the independent variable time t, the signals are classified as continuous time and discrete time signal, which we have discussed in the previous class itself. And based on the amplitude value of a signal in positive time axis and negative time axis, the signals are classified as even and odd signals. And based on the periodicity nature of these signals, we can categorize the signals as periodic and non-periodic signals. And based on the behavior of the signals are classified as deterministic and random signals. And based on the energy and the power content of the signal is classified as energy and power signal. So this is the basic classification what we have for signals. So let's take up this one by one. Now the first category of the signal what we have is continuous and discrete time signal. So continuous time signals are always represented with the variable t, and discrete time signals are represented with the variable en. So you can, as told in the previous class, you can use any of the alphabet from A to Z for the representation of the signal. So standard representation what we are taking for input is x. So here two signals are represented in continuous and discrete form. In the last class I had explained about sampling process, which is going to convert the continuous time signal into a discrete form. So here, by replacing the variable t, this variable t with n into t, the discrete time signal can be obtained, where Ts is named as the sampling frequency, which is taken as the reciprocal of the sampling frequency Fs. So this figure is showing you the continuous time and discrete time representation of a waveform. So in the continuous form, your x of t will have a signal value at all the instant of time t. It is continuously defined without any break. Whereas the same signal is represented here in the discrete form, wherein we have samples at discrete instance of time like 0, 1, plus or minus 1, plus or minus 2, 3 and so on. So this is the first classification what we have based on the time period. The second category of the signal what we have is even and odd signals. So even signals are those which are symmetric about the vertical axis or vertical time axis, which means that if I have the same value of the signal, please refer the signal x1 of t here. If you can see, the magnitude of the signal is A and it is in the rectangular shape with the time duration 0 to t1 by 2. The same value of the signal, if it is available in the left time axis or towards the negative time axis, then it is said to be an even signal. So which is represented like this. So here you can see x of t is taken as equal to what? X of minus t. If this representation is known, in the even form, the signal x of t is symmetric about the x-axis, which is represented as x of t equal to x of minus t. This indicates that the negative time axis and the positive time axis should have the same part of the signal. So that is called a symmetry property. So any signal which is symmetric with respect to the time axis is considered to be an even signal. So similarly, if I consider an odd signal, in case of odd signal, the signals are asymmetric about the vertical time axis, which is represented as x of minus t is equal to minus x of t, which means that whatever signal I have on the positive time axis, exactly the reverse version of the signal will be there on the negative time axis, which means that if the amplitude of the signal is A on the positive time axis, here merely it will be minus A. So those signals are classified as even and odd signals. So even signals are symmetric signals, odd signals are considered to be asymmetric signals about the vertical time axis. So simple example which I can quote for an even signal is sinusoidal signal, because sine of minus theta is always equal to, cos theta is considered to be an even signal, because cos of minus theta is always considered to be even in nature, because cos of minus theta gives you cos theta itself. Similarly, sin theta is considered to be an odd value, because sin of minus theta is taken as equal to minus sin theta. So when we replace the variable with a negative value or negative time value, then the amplitude goes negative in terms of your odd signal. So this is the classification of the signal based on the symmetry property. This is the example which is showing you where your sine signal is considered to be an odd signal, because if you replace t with minus t here, it is going to take the value as minus sin pi t by t. So hence sine is considered to be always an odd function. Now this is very important from the examination point of view, because one question will be asked on this. See, when we consider any signal, it can have an even and an odd part in it. We exactly don't know. So if I am decomposing my signal as an even part and an odd part, which is defined as x of t equal to xe of t plus x odd of t, then from the evaluation we can get the even component of the signal xe of t as equal to half into x of t plus x of minus t. So please do remember this formula to evaluate the even component of a signal. And similarly, the odd component of a signal, continuous time signal x of t, is represented as x o of t equal to 1 by 2 x of t minus x of minus t. So these two formulas are used to evaluate the even and odd component of a continuous time signal. Similarly, the same thing holds good for your discrete time signal also, where we can determine the even and odd component representation as xe of n and xo of n, which can be taken as equal to half x of n plus x of minus n, and xo of n can be considered as half x of n minus x of minus n. So this is about even and odd signals. Now let's move on to the next category of signals what we have, that is periodic and non-periodic signals. A signal is considered to be periodic if it satisfies the condition that x of t equal to x of t plus t for all t, where capital T is considered to be the fundamental period, which is taken as equal to 1 by f, or f is taken as equal to 1 by t. Okay. So if a signal gets repeated after a particular interval of time, those signals are considered to be periodic. So in the continuous form representation, I am representing the periodic signal as equal to x of t equal to x of t plus capital T, and the angular frequency corresponding to this particular continuous time signal is represented as omega equal to 2 pi f in radians per second. So a signal that doesn't satisfy this property are classified as non-periodic signals. So non-periodic signals will not have the same value which is repeated at a particular instant of time. So they will take a different value at different instance of time. So those signals are considered to be non-periodic. The same thing holds good for the discrete time signal x of n also. So if I am considering a discrete time signal x of n, then to check the periodicity, I am going to consider x of n as equal to x of n plus capital N. Let's take examples on these periodic and non-periodic signals in the next slide. So here I have a rectangular pulse which is getting repeated. As you can see, if I consider this one cycle, so positive rectangular pulse, negative rectangular pulse with an amplitude varying from 1 to minus 1. So the time duration is from 0 to 0.2. So this is taken as the fundamental period, and reciprocal of this will give us the frequency and the same shape of the signal is getting in the next instant of time. So 0.2 to 0.4, difference is 0.2, again here time period is 0.2, and from 0.2 to 0.6 you can observe the same signal which is getting repeated. So this is a rectangular pulse which is periodic in nature. So any signal which has a repetition of the same value after a particular instant of time could be considered as a periodic signal. But the same shape, if it is represented only with a single pulse like this without any repetition, then this is considered to be a non-periodic signal. So similarly we can quote other examples also. So here as you can see, so this is one example for you where I have a triangular pulse which is again getting repeated at an instant of time 0.2, 0.4, 0.6, 0.8 and 1. Okay. So your task is to find the expression for the fundamental frequency in terms of hertz. So if you can see here, the fundamental period is 0.2 and the reciprocal of this will give you the fundamental frequency of the triangular pulse. So I hope you have followed the basic concepts of periodic or non-periodic signals. So sinusoidal signals, cosine signals which are getting repeated after a particular instant of time will also come under this category. So answer for this particular example is the frequency is 5 Hertz because time period is 0.2, reciprocal of that will give you 5 Hertz as the fundamental frequency. In the discrete form, we are going to represent a periodic signal with an expression as x of n is equal to x of n plus capital N, where n is an integer and capital N is the total number of samples that we can have in a particular period with repetition. So please do observe this waveform. So here as you can see, one cycle if I am considering here, so I have 4 samples with amplitude as 1 and 4 samples with an amplitude as -1 and it is getting repeated. So totally I have 4 plus 4, 8 samples and this becomes here capital N. So for this example, capital N is 8, which is considered as the number of samples. Okay, so here we are not going to talk in terms of time and seconds. Here we are going to talk with respect to the number of samples that we can have in a particular discrete time signal. So here the fundamental period is considered to be 8 samples. Please do remember this. If a signal is periodic, we are going to find the fundamental period corresponding to a discrete time signal as equal to the number of samples that we can have in one period of time. Now here this is an example of a non-periodic signal where you have only 3 samples from -1 to 1, there is no repetition. So these two could be considered as an example for periodic and non-periodic signals in the discrete form. A question is given here to determine the periodicity of a signal. So there are variety of continuous and discrete time signals which are listed here. So first signal is x of t equal to cos square 2 pi t. Second signal is x of t equal to sin cube 2t. And discrete time signals are represented as -1 to the power n, x of n is equal to cos 2n and x of n is equal to cos 2 pi n. So our task is to find the fundamental periods. For the first one, if I take coefficient of t is 2 pi, if I take coefficient of t as equal to 2 pi, your omega is considered as equal to 2 pi. Sorry, my f will be considered as equal to 1. So we will be getting the time value as equal to 0.5 pi seconds and 2 samples, and the next one is considered to be first one is having a time period as 0.5 seconds, second one is having a time period as equal to pi seconds, the third one is having that fundamental time period as equal to 2 samples, the fourth one is non-periodic because we have 2 pi, there is 2n, pi is missing, and the last signal is having the number of samples as equal to 1 here. So we will discuss about these problems in detail in the coming classes. So just make a note of it. Coming to the next category of signals, we have deterministic and random signals. So deterministic signals are those where there is no uncertainty with respect to its value at any instant of time for a specified function. So it means that the signal will have a definite value at any instant of time t. So those signals are categorized as deterministic signals, whereas random signals are those signals where there is an uncertainty of the value before its occurrence. So all signals except noise signal is considered to be deterministic in nature. Only the noise signals are those signals whose behavior cannot be judged. Okay, so that is the only signal which comes under random signals category. So this is a simple definition of deterministic and random signals. The next classification is named as energy and power signals. So energy signals are those signals which have a finite energy and zero power. So power signals are those signals which have a finite power and infinite energy. So based on the energy value and power value, they are whether finite or infinite, we can classify the signals as energy signals and power signals. So one important hint of what you need to remember when you are classifying the energy and power signals is all periodic signals are considered to be power signals and all non-periodic signals are considered to be energy signals. So there are two formulas which is used to evaluate the energy and the power value of a signal. So energy value of a continuous time signal is evaluated using the first formula, where E is taken as equal to integration from minus infinity to plus infinity x square of t dt. And for a continuous time signal, if a signal is periodic, then the power value P is given as equal to 1 by t integration from minus t by 2 to plus t by 2 x square of t dt. So similarly for discrete time signals, the energy of integration is replaced by summation here, where E is taken as summation n ranging from minus infinity to plus infinity x square of n, and the power value is taken as 1 over n summation ranging from 0 to the upper limit x square of n. So using these four formulas for continuous and discrete time signals, we can evaluate the energy and power. So based on the energy and the power value what we can get, we can classify the signals as energy and power signals. So this is what I just now told you. X of t or x of n is said to be an energy signal if and only if the energy value E is between 0 to infinity and the power value should be 0, and all non-periodic signals are considered to be energy signals. So please make a note of it. And similarly, a signal x of t or x of n is said to be a power signal if and only if the power value is finite, that is if it ranges between 0 to infinity, and energy E should be always infinite. So all periodic signals are said to be power signals. So the signals that doesn't satisfy either of the conditions are said to be neither energy signals nor power signals. In today's session, I have given you a brief overview of classification of signals into different categories based on their behavior, based on their value, based on the magnitude and independent variable. I hope you have understood the basic classification of signals and systems. So this basic knowledge of signals and systems, what you have learned in today's session, is very much important, because the further topics what we are going to discuss will be based on the different types of the signals which we are going to handle. So this could be asked as a theory question in the examination also for 6 to 8 marks. They might ask you to explain the basic classification of the signals into different categories, or they might give you a comparison kind of question where you may have to compare an even signal with an odd signal, or an energy signal with a power signal, or a periodic signal with a non-periodic signal. With few examples you need to quote. So please do pay concentration on this particular classification of signals. So the topic is very much important from the examination point of view. So I hope this session was interesting and you are able to get a basic knowledge about the variety of signals that you can have in your operation. So thank you for your valuable time. Have a nice day. In next session, I will start with the basic elementary signals which are used here in the signal operations, and along with that basic operations on time and independent variable time and dependent variable amplitude will be discussed in the next session. So thank you one and all. Have a nice day.